This video tutorial explains the basics of the FS5 operation for steady-state fluorescent measurements. This diagram shows you the basic architecture of the FS5. In blue you can see the excitation light path, and in red the emission light path. At the left hand side you can see the sources, and at the right hand side the detector. In this area you can see the sources. The larger lamp is a 150 watt xenon lamp used for steady state measurements, and the smaller lamp is the microsecond lamp used for microsecond lifetime or MCS measurements. They are separated by an off-axis elliptical mirror which allows you to switch between the lamps. This shows you the excitation monochromator. It is a 225mm focal length Czerny-Turner monochromator. It has two spherical mirrors and a grating. The excitation shutter is used to block the light from coming into the monochromator. And you can see on the exit of the monochromator we have excitation filters. These are long wavelength pass filters used for suppressing second order and harmonic effects. This area shows you the sample chamber and the optics around the sample chamber. You can see we have a liquid sample holder in just now with a cuvette inside. You can see that on the blue path you have a reference detector which is used for correcting the excitation spectra. You can see some of the blue excitation light passing through the cuvette. That is light which hits the transmission detector, which is used for measuring absorbance. The two mirrors you can see either side of the cuvette are toroidal mirrors, and they are used for correcting off-axis aberrations in the optical path. The emission monochromator is very similar to the excitation monochromator. It has an emission shutter which is controlled by the sample chamber lid, and also a set of emission filters which are used to suppress second order and stray light effects. At the exit of the emission monochromator, this is where the detectors are located. The FS5 has space for two detectors, and they are usually PMTs or photomultiplier tubes, covering a variety of spectral ranges and response times. This shows you the actual sample chamber or sample cassette in an FS5. You can see the light passing along the excitation path through the cuvette to the transmission detector. Here we can see how easy it is to change a sample cassette in an FS5. First you unscrew the sample cassette and pull it out. Fluorical software will automatically recognize when you remove the sample cassette and also when you put a new one in. It will recognize exactly what cassette has been taken out and exactly what cassette has been put back in. When Fluorical is launched, the signal rate window appears in the middle of the screen. In order to look at the signal on the transmission detector, choose Options, Signal Rate Options, and tick the Display Transmission Signal. You will now see a third bar on the signal rate screen. The signal rate screen is by far the most important screen in Fluorical software. It shows you what source light path you use. It shows you what excitation and emission wavelengths you choose and what bandwidths you're using. It shows you the detector light path as well as a signal on all three detectors: excitation reference, transmission, and the emission detector. The center wavelengths for excitation and emission can be moved up and down using cursor keys. By doing a right click on the mouse, you can also change how much the step sizes are, as well as entering a value manually. The signal rate screen gives you the current status of the instrument. It shows you what excitation and emission wavelengths and bandwidths you're using. But most importantly, it shows you what signals you have on the detector at any one time. So before you make any measurement, the signal rate window should always be consulted. The signal rate window should also be used to protect against detector saturation. When the counts go red, then we lift the sample chamber lid to bring down the emission shutter and protect the emission detector. The signal rate window is used to set up each measurement and to make sure that all three detectors have a good size signal. We can adjust the bandwidths to make the signals larger or smaller. After we are happy with the signal size we see, we use the lambda menu to choose any one of the steady state scans. If we choose an emission scan, you can see the excitation and emission parameters and bandwidths all come from the signal rate window. Pressing the apply button saves the changes you made until next time, and pressing the OK button will begin the scan. Once the emission scan is finished, you can see the properties are displayed down the right-hand side of the spectra. Making an excitation scan is just as simple. You have the same emission wavelength that you chose in the signal rate window, and you set up the excitation wavelength from start to finish with a step size, dwell time, and number of repeats. You can also choose to have excitation correction, which corrects the excitation spectra using the reference detector. Again, the properties are shown down the right-hand side of the spectra. Once the scans are finished, we can tell them to look at them like this. And if you do right-click, select Properties, it tells you all the details of how the scan was made and when it was made and whether it was corrected. There are a number of other options you can choose to analyze the spectra in many different ways. We can also combine the spectra with one button and then normalize the spectra to a certain value. This is useful for publications. Florical software also has many analysis, presentation, and manipulation features. One of the most common features that customers use is the emission map. So this is a series of excitation scans at different emission wavelengths, or a series of emission scans at different excitation wavelengths. Either way, it is a complete fluorescence map of the sample. The emission map also allows you to automatically avoid first or second order scatter situations. The emission map shows you the complete steady state fluorescence for that sample. We can look at the properties of each scan individually. And if we wish, we can also do the correction for all of the scans together or one scan at a time. We can see that in this situation, first order scatter has been avoided by changing the start wavelength of the emission scan. And certain emission scans will start at different emission wavelengths. The emission map can also be rendered in a number of different formats. Here you can see the 3D representation. In the 3D representation, looking along one axis shows you the excitation spectra. Whilst looking along the other axis shows you the emission spectra. The emission map can also be rendered as a thermal graph. And by clicking on this using the Control key and the Shift key, you can change the location of the X and Y axes. There are also some other analysis options. You can use chromaticity analysis, as shown here, where the spectra is represented on CIE X and Y and U and V axes. The user can also input reference values which the CIE coordinates can be compared to. When we put a new sample into the FS5, we consult the signal rate window. We can choose the excitation and emission wavelengths and bandwidths. On the emission scan setup, you have a correction tab where you can choose to have excitation, emission correction, and background subtraction. The emission tab shows you the scan from and to wavelengths, as well as the step sizes and dwell times. The number of repeats is the number of times the scan will repeat. And also the dwell times are cumulative. So if you do 2 scans at 0.1 seconds, the total dwell time will be 0.2 seconds. You can see the feature on this scan, the small step around 400 nanometers. This is caused by the engagement of the emission glass filter for suppressing second order effects. So it's very important that you perform emission correction on this spectra in order to correct out or remove this step. Equally, for an excitation scan, you have excitation and emission tabs. The excitation scan parameters are the same, which wavelength from and which wavelength to. They also show you the step sizes and dwell times. The program allows you to easily normalize different scans together and also perform data manipulation. The transmission scan makes use of the transmission detector and is used for measuring the absorbance of samples. In order to make this measurement, we measure two things. One, sample in solvent, and a second scan just measuring the solvent. Once we've measured both scans, we overlay them together in the same measurement container. We can name the scans appropriately. And then we perform the absorption analysis. We tell the software which scan is the solvent, and it gives you a graph of absorbance against the wavelength. Multiple measurements allow you to do a number of repetitive scans. So, for example, to measure the same emission scan 10 times with 6 seconds between each emission scan. This is useful if your sample has any kinetics or photobleaching. The last type of steady-state scan that can be used is the kinetic scan. This is a very simple measurement where the counts on the PMT are measured for a certain length of time, for example for 100 seconds at half-second intervals. The interesting thing is that you can also control the excitation shutter to control the illumination of the sample for fluorescent excitation. This type of measurement is very useful if you have samples which have very long phosphorescent lifetimes.